Okay. Okay, so I'm recording, so I guess everyone that's not here, they'll be able to see the announcements about the exam. So, just to start, the exam one, average. So if you didn't do well, don't feel bad. It was a 49.7, so 50%. But the highest score was a 97. Oh. So it is possible, but if you did poorly, don't feel too bad. But you guys did have the material. Like, it wasn't like there was something missing that you guys didn't have. But again, just don't feel bad. Let's see. There's a lot of things to talk about. You guys are probably wondering what happens next, right? Like, what do I do if I didn't get a good score? First couple things about grading is problem. Sorry, which number was that? The one that I changed the grading scheme.
CQ
4.
3.
CQ3. It was originally 20% of the exam. It was, each of the concept questions was around 20 points. Sorry? CQ4. Oh, it is CQ4? Okay, CQ4. And it was the oblique impacts one, where it's, asking about what direction momentum's conserved. That one, if you did really bad, it was really screwing up some people's grades where they did good on the rest of the exam. Oh yeah, you can get your exam if you want. I guess right now while I explain, it's fine because I'm not going to be really writing any math on here. But if you got it like a 0 out of 20, I changed it to be out of 10 for CQ4 instead of out of 20. And then I made your exam out of 90. So essentially, I made this problem worth half as much for your total exam. And that helped some people. Other people it didn't help, so I didn't change it. Like, if you got a 20 out of 20 on CQ4, then I didn't change the amount of points it was worth because it was helping your exam. Also, the extra credit helped a lot of people, so if you did that, good job. And let's see, what else? I have not decided if I'm going to curve or if I am going to allow you guys to make up the whole test with one problem on the final. I am thinking of doing one of those two. I will decide, but this is likely not going to be your final grade unless you did very well on this exam. So what that would look like is, a standard curve, or you can prove that you did learn the material by the end of the course by picking one of the problems on the final that is this material, like obviously not a rigid body problem, but one of the problems from the first half of the course. And if you did really well on that problem, then it will replace your exam 1 score. But also remember, exam 1 is only 15% of your grade. Well, only, I guess that's still kind of a lot. But it's going to be either one of those two. I haven't decided yet, but I think, well, let me just take a vote. Who would prefer a curve who would prefer replacing your exam score with one test on one problem on the final? Some people. Who would prefer a curve? Okay, so a lot more people prefer a curve. I thought it would be the other way around because you have the potential to get like 100% on your, if you replace it. So, question?
Like if the average is a 50 and you curve that to a 70, then everyone in the room would have a 70, right?
On average, yeah. But then the people that were, really low then still don't have a chance to.
Well, then they have a 50. It's not like a 25.
Okay. Yeah. I'm glad I asked, 'cause I thought you guys
Yeah.
would prefer the other. So I'm gonna think about it. I'm gonna talk to some other lecturers, see what they do. But it's not this, nothing has been curved yet. So, don't worry. But that leads me to, what went wrong on the exam for some people. Like I said, some people nothing went wrong. Well, one thing went wrong where the math, where they made a major math error. But let me go over some of the core concepts that kind of went wrong. So one of the main things, and this is what other lecturers have told me, is the number one thing you guys should learn from this course is free body diagrams and mass acceleration diagrams. FBDs and MADs. And this was where people probably struggled the most on a lot of the problems, where they'd write their FBD and they'd write their MAD, and the first thing was they wouldn't draw the body fully isolated. They might draw it like on the beam still, but a free body diagram is a free body. Like it needs to be isolated so that you can apply all your forces. And another thing was just people missed a lot of forces. So, for the plane, for example, at point B, you're gonna have, gravity coming down, the force of the seat pushing up, the force of the seat pushing to the side, and for your mass acceleration diagram, you're going to have MA here and MA here. But this acceleration was negative because they were decelerating. But people just missed a lot of forces and accelerations on their diagrams, and that's something I think you guys should. Question?
Sorry, what was the force going backwards? On the
I'm talking about point B.
Oh, okay.
This is the normal force in X, and this is the normal force in, this is mg, and this is the normal force in Y. I'm going to go over this problem on its own eventually, but I'm kind of going through one problem from the midterm per class. But yeah, I think people just really need to work on their free body diagrams, because if you don't have all your forces, then all your math just gets messed up. So, practice your free body diagrams. Another thing was, these MADs and FBDs is F equals MA. And some people were putting velocities on here, like V1 or, Vy or Vx. Just for example, not specifically for this problem, but they put velocity in their mass acceleration or FBD, and then they'd say V was equal to MA, and that just doesn't work. That's not F equals MA. So there's kind of a core conceptual misunderstanding there that, relating the wrong thing here. Another problem that happened with some people is they just forgot the mass, and they just said force was equal to acceleration. So that's kind of another core conceptual problem that a lot of people are missing. Let's see. But yeah, FBDs, MADs. I think this is probably the number one thing everyone needs to practice. And then another area that I think a lot of people struggled with was polar and path, so angular stuff, where sometimes people would think that alpha was the same thing as acceleration, where alpha is angular acceleration in radians per second, and acceleration is just radians per second squared, meters per second squared. These are not the same thing. One is an angular acceleration, the other is linear. So this was another common thing that I saw. And let's see, which problem was this? Another one that I saw, especially on the last problem a lot, was people were using this equation on the equation sheet. V squared over R is equal to R times theta double dot squared. This is just a definition of theta dot squared. This is just a definition of theta dot because theta dot, or V, is equal to theta dot times R. Sorry, I keep writing not what I say. This is just a definition. This equation is just useful for converting between using theta dot or V for path or polar. It doesn't really give you any new information. This is just nomenclature. And some people were trying to use this to solve the last problem, and it just wasn't working out. So that's another thing that some people struggled with. And I'll talk about the rest of the typical problems as I go through more of the problems in class. Let's see if there was anything else. Okay, and now I'm just going to talk about, I don't know how to say it, just study habits and how to prepare for exams like this. I think in a lot of classes, it's pretty normal to just look at the material and review it, and that's enough for the exam. But in a class like this, like dynamics or I don't know, fluid mechanics or something like that, you need to quiz yourself before with the homework problems. If you look at a homework problem and just review it and look at the solution and say, oh, I know how to do it, I'm good for the exam, you're not going to remember it. You need to go through the homework problems and use them as like a quiz. You don't have to do every single one, but pick like one from each homework problem or one type of problem and try to do it without looking at anything. Without looking at any solutions. And if you can't do it, then you're probably not going to be able to do it on the exam. And then the ones that you struggle the most on, pick more of those problems to practice, and then you should be prepared for the exam. But my point is that all of the concepts on the exam were in the homework. I don't want to say, oh, you guys should have known how to do this. I know it's really difficult. Like, I'm not saying, you should have been perfect or anything like that, but I'm saying for future exams, try to quiz yourself. That is what worked best for me, is quizzing myself off of the homework problems and then seeing where I didn't do well and practicing more. And again, like I said at the beginning of the quarter, you just have to practice it. You can't review the solution. You have to do it, and that's the only way you're going to remember. You have to get in that space where you're stuck for a long time, feel really uncomfortable, and it's really annoying and frustrating, but then you remember. And that's really my best recommendation. So any questions about the exam or any notes like I didn't think that was fair or whatever?
Sorry, this is kind of like a thing on the final, but are you curving our class individually, or is it a curve against everyone?
No, I get to curve your guys' class individually.
Okay.
I have control. Like I am going to grade you guys based off of what I think your performance was in this class, not versus all the other classes. Question?
Do you get to grade our finals, or is it?
That's a good question. That's a good question. I don't. So I get to grade one of the problems on all of the section's finals, which kind of sucks for me because that means I have to grade like 200 problems. Question?
Did you feel yourself like giving out a bunch of pity points on the?
A little bit. So I think that's a good question. Is the way that I graded gonna be similar to the way you're graded on the final? I think the final might be a little harsher. So yeah, take that as you will. But I am going, there is going to be a curve for the class, and it's just this class. It's not everyone else. So, and I'm going to decide, for this exam, like I said, I still haven't decided if I'm curving it or I'm going to let you replace your grade or both. I'm going to talk to other lecturers and see what. Yeah, both? Yeah, I like both, right?
Keep like the one that's like better? Yeah. All right.
But okay. I was going to go over more material today first, but I think since we're on the topic of the exam, I'm just going to go over the exam problem, one of the exam problems. So this one, because we've done the first two so far. There weren't many people in class yesterday, so you might not have seen me going over the one last class, and the video from last class didn't record everything, but I do have the solution posted online if you want to see the solution. But this one, I think the tricky thing with this one was knowing, if you write out your equation T1 plus V1E plus V1G plus U1 to 2 is equal to T2 plus E2E plus V2G. Yeah. So another thing, and this is, learning what works for you for testing. But a lot of people, not a lot, but a few people thought that it wasn't in the horizontal plane, but it was, so there was no gravity. And then there was no spring either, so these were 0. And another one that some people didn't see that's just written is it starts at rest. So you immediately get U1 to 2 is equal to T2. And I think where people struggled is realizing that this is 2 terms, not 1 term. There are U1 to 2 can be multiple forces acting on the body. And that means you have your friction force, U1 to 2 friction, plus U1 to 2, F of x is equal to T2. And so that's the first thing, but I think people kind of struggled on what the definition of work and energy that we went over was, because we used a lot of these on the homework where it's pre-derived for you. The value of energy from gravity or the value of energy from a spring has already been integrated. But if you have just a force, you have to integrate it. You can't just say the force times the distance is your energy if it's a non-constant force. So let's just look at the first one, F of x. So we have the slider going on a path like this. And there's a force that depends on x as you move through the path, and it is 3x minus 2e to the x. I thought that making that really complicated, most people would understand that you don't need to evaluate that integral. A couple people did. I'm sorry that you did. But I thought about making it even more complicated and just saying like hyperbolic sine or something, just to make it clear that you don't need to integrate it. But most people, that was clear. So this is 4 and this is 5. So the reason why I put a distance here and here is for people to choose, or for people to see or decide which direction that this needs to be integrated over and what your limits of integration are. So if you remember from the slide before, if we have from a previous lecture, if we have a force, let's say there's a velocity in this direction, or this is the path that a particle follows, and the force is here, then the component of the force that does the work, that contributes work, is only the component that's parallel to the displacement, right? Like this component of the force that's perpendicular to this displacement does not contribute any work. So the fact that the force is pointing completely horizontal means that any displacement in this direction, there's no work done by this force. It's only this displacement, right? So, and because it's not constant, you have to integrate, where the work is, the area under the curve of force and distance, right? So you have to integrate to find this area. So you would get integral of f of x dx from 0 to 4. And this, you guys got major points if you got this 4 right. That was one of the main things I was looking for. Some people put 8 instead of 4 because they integrated over the length of the path. But that would say that your force is always directed in the direction of the path, but it's actually only ever this way. But that leads to the second term, which was the friction term, which in the book they put a little prime here for U1 to 2 prime for non-conservative forces, where they're always in the direction of the path. The friction is always pointing this way, against the path. And so the friction, you could say, it's the integral of f friction ds from 0 to 8. But the friction's constant, so you can just say it's the force of friction times 8, which was, I think it was 5 newtons times 8 meters. And that would be this term here. So those are some, I think those are some pretty important conceptual ideas, especially for the force. It has to be, you have to integrate it over the direction that it's pointing. And same with friction, it's always pointing the opposite of the direction. So, you're just going over this distance, force times distance, 5 times 8 meters, right? Question?
It'd also be negative too, right?
Yes, and it's negative. And the easiest way to think about that is you're starting at rest and you're getting some velocity at the end because this force is pulling on it, right? And any energy imparted from this force is going to be lost due to there's going to be some loss due to friction. So you're going to get a negative sign here, right? So because if you didn't have friction, it would be going faster at the end. So you're going to have a negative sign here. Any other questions about this problem?
I'd like to point out the function that you chose actually has the force pointing backwards the whole time.
Because the 2e to the negative 2e to the x is
always
larger.
going to be larger than 3x.
That's a good point. But I gave you the direction though, so and nobody nobody did that wrong. But that is a good point. That is a good point. I mean, if you really did evaluate all of it, you'd probably get a negative here.
Yeah.
But yeah, that's a good point. And I did have this reviewed, and even my other lecturers didn't see that. So good point.
It took me looking at it for half an hour.
Yeah. Yeah. Any other questions about this problem? No? Okay. Then we're going to move on to the lecture material for today. Okay, today I'm not going to really introduce any new concepts because I'm just helping prepare you guys for the homework that's due tomorrow night, not tonight. I changed it in case anybody didn't get that last time. And so last time we did this problem that's linkages, and we're asked to find the acceleration of the different linkages, right? This problem is basically the same thing, but it looks scarier because, you know, you have, oh, this is like rolling down this hill, this is moving to the right, I don't know what to do, this is a weird situation that I haven't seen before. But the easiest thing to do with these is notice what shape is this? This is a circle. This is a circular arc, right? And it's going to follow this circular arc. So the easiest thing to do with this problem is to just say that this is another linkage here. Because it's following a curve, right? And so now it just looks like any other linkage problem that you've seen. And but I'm going to do it again because, again, not many people were here last week, and I think repetition is going to be helpful with these kind of problems. So again, the first thing we have to do with these kind of problems is find angular velocities first before you can find accelerations. So again, they're asking us to find the angular acceleration of the bar because A is moving to the right. And they're asking us to find the tangential acceleration of point B. And I guess let's talk about that first before we start. A is here, B is here. So does anyone have an idea of what direction the tangential acceleration of B is along the path? This is down?
No,
Like this way?
yeah, following the curve.
Yeah, so it's going to be following the curve, right? Which is just going to be, if you have an omega here and an alpha here, then this is going to be alpha times r, at least in magnitude, right? Or alpha cross r if you want your magnitude and direction. But this r is going to be, I'm going to call this O, point O. This r is going to be B with respect to O, not B with respect to A. Because they're asking along its path, determine the tangential acceleration of point B along its path. Not so they're referring to the path that it's rolling on, not the tangential acceleration with respect to A. Does that make sense to people? Okay, so first things first, we need to find velocities. And again, treating this distance O and B like a link, you'll get an omega there. Even though there's an invisible link here, there's no link, we can say that OB is a link and you're getting an omega for OB. So let's see. And the way we always start these, or the way that I always start them that I find useful, is if you have two links, write an equation for the velocity or the acceleration of the point that's joining the two links. And start from the point where you have a known velocity, because that's what's driving the system. You can start from here and go this way in terms of the order that you solve for values for the links. But for me, it just makes the most sense to start from A, because that's what's driving the system. So it's the most intuitive to me. So if I write VB with respect to A, this is equal to, you know, would they give us the velocity for 3 meters per second? 3I hat plus omega AB cross RB with respect to A. And one thing I want to note is the subscripts for omega don't matter. Order doesn't matter. And the order doesn't matter because it doesn't matter if you're looking from this direction or this direction. The omega of a link is always the same. For any point, any direction you're looking, the rotation of the link is always the same for the entire rigid body. That's just definitions of rigid bodies. So I could call this AB, omega AB, or omega BA. It doesn't matter. But this direction does, where RB with respect to A is pointing this way. Question?
Yeah, kind of like this was kind of confusing me on the last homework. So it's like it's not rotating around a singular point, or
Yeah. So this link is undergoing general plane motion. So it's both translating and rotating. And when you have that, then that means it's rotating about some point somewhere else off in space. That was the concept of instantaneous centers, where if there is a point on the link that's fixed, it's only rotating about this point, right? And then it's just, you know, doing general rotation, right? But if it's rotating and translating, then it's as if it's rotating about a point like that, right? Does that answer your question?
Yeah.
Or
yeah, that makes more sense.
so RBA, they give us the dimensions, which is just geometry. Let's see. And this RBA becomes negative 1.17 I hat plus 0.25 J hat. And yeah, the finding RBA was a little tricky because you had to, I found this angle here and did sine and cosine to find the distances. Question?
I'm pretty sure it's easiest just to, you know that the radius is half, and then you just subtract the cosine of 60 from that height, and then you have the hypotenuse and the smaller leg, and you can use a trig to find the bottom leg, and that you don't have to find that.
Oh, yeah, you can do it that way too. You're better at this triangle stuff than I am. But either way, it's just finding the two sides, right? So this is what I got. And again, I want to kind of go fast through the angular velocity part because I did that. We've done that before, and I want to get to acceleration. So if we get this, again, now we have to do the cross product table because R has two components. If you really wanted to be fancy, you could rotate your coordinate system to be something like this, so that R is just one direction, but then your A value velocity is in another direction, so it has two components, so it doesn't really help you. So we're just going to say this is X and Y. And I should have written this beforehand. This is something I tell you guys to do on your exam. Write your coordinate system at the beginning. So omega AB cross RB with respect to A is equal to the determinant of I, J, K, 0, 0 omega AB, and and this is equal to and something to remember here, this is what we do, this is what we did with these kind of problems last time, is if you don't know your omega, just assume that it's positive, assume that it's going in the right direction, that this is a positive k. So I have a positive here, and you get, after you do your cross product, it turns out like this, right? And then if it's actually rotating the other way, then at the end of the problem, you'll get a negative. And something that helps me with these problems is as I'm going through it, kind of double checking if these things make sense by looking at what I think the omega is going to be. In this problem, I would assume, this B is going down, A is going to the right, so I'm going to assume that omega is going to be, or I would think that omega would be counterclockwise, right? So at the end, we'll see, if it's negative. If it's not negative, then that's a good way to know, I think I did something wrong and go through. The easiest place here is to miss this negative here because, if you cover up this term is minus j hat times a minus this term, and you just get a bunch of minuses, and it just gets really tedious carrying all the signs. But let's see. So if we have this, and we have this, and we have this, we get our. I'm going to erase this step one. Our first equation, which is VB I hat, is equal to negative 3 I hat minus 0.25 omega AB I hat, and then V, equation 2, VBJ is equal to negative 1.17 omega AB J hat. And these, notice here, I'm not putting a vector symbol over these guys because these have an I hat attached or a J hat attached to them. And we've already done the cross product and we're just trying to find the value of this guy, right? But these all have vector symbols. So this was for the first link AB. We found the velocity. Now we're going to do link OB. And it's not really a link, but we're treating it like a link. And we can say VB is equal to VO minus 0.25. Oh wait, it's giving me that. And for VO, so we're finding the velocity of O or of B with respect to O. VO is just 0 because we're assuming it's a pinned link here, and then you get this guy where R, B with respect to O, points this way. I'm going to save you guys the geometry of that. That's just VB is equal to well, I'll tell you what R is first. R, B with respect to O is equal to negative 0.433 I hat minus 0.25 J hat, and we do omega OB cross R, B with respect to O is equal to the determinant again, assuming that omega OB is a positive value, and we get negative 4.3 0.253, negative 0.250. And again, just explain, even though I just gave you guys these values just now, I didn't calculate them out on the board. These two negatives make sense because our B with respect to O is going down and to the left, right? So we expect both of these values to be negative. And when doing the determinant of that, we get that it's equal to 0.25 omega OB I hat minus 0.433 omega OB J hat. And that gives us another two equations for VB for the I and J direction. So VBI is equal to 0.25 omega OB I hat, and VBJ is equal to negative 0.433 omega OB J hat. And this is our equation 3 and our equation 4. We have 4 equations and 4 unknowns. We don't know the two components of the velocity of B, and we don't know omega OB and omega AB, and we can use that to solve everything. And I'm just gonna solve that for you. Solve dot 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 omega AB is equal to 2.234 radians per second. And again, the omega is radians per second. I think a useful thing about the midterm is that I was saying earlier about the midterm is knowing what your units are on each side of the equation. You know, this is radians per second, this is meters per second, so they should never be equal. And omega OB is equal to 8.767 radians per second. So we're halfway done, right? We have the omegas, now we need to find the alphas because that's what they asked for. So let me erase this guy. X, Y, plus. Okay. So we just do the same thing. We do the except we do the acceleration of B for each link question.
Yeah, real quick. For link AB, the equation 1, VDI, why is it negative 3? That means negative 0.25.
Good question. Did I write it wrong?
The negative 3.
Yeah.
Yeah, it shouldn't be
Moving
negative.
to the right.
Yeah, this should be positive.
Yeah.
Good catch. Okay, there's a lot I want to still cover, so I'm gonna try to blast through this. So acceleration. Writing an equation for AB is equal to A plus alpha AB cross R B with respect to A. And so this is for link AB. And the acceleration of A, they tell us it's at constant velocity, right? So the acceleration of A is going to be 0. So we get AB. And we already determined what RB with respect to A is. We set it over here, negative 1.7, 0.25, right? And so we do the exact same thing. This is also K, alpha is also K, right? So we just do the same determinant cross product here. And I'm just gonna write it out for the sake of time. We get alpha AB cross RB with respect to A. Oh, I totally forgot omega AB R B with respect to A. don't forget this guy. I almost forgot that because this is the equation for acceleration. And so there's two terms here. There's the, I just want to go over this again. This is normal acceleration, AN, and this is tangential, AT. And we're going to use this for this link at the end. We're going to just plug in the alpha that we find for link OB into this tangential term, and that'll give us the solution we're looking for. But save some time, this just becomes negative 2.234 squared times negative 0.433 I hat minus 0.25 j hat plus alpha AB cross RB with respect to A. And I'm not going to do this for you guys. I'm just going to assume that we did this cross product and we get our two equations for AB is ABI is equal to negative 0.25 alpha AB I hat plus 2.16 I hat, and ABJ is equal to negative 1.17 alpha AB J hat plus J hat. And so one thing to note just about what these look like, when you're writing the acceleration for a point on connecting two links, you should get just a value for one of your terms because that's coming from your normal acceleration and you have your omega that you're squaring. You have all of these values, so there shouldn't be a variable in these terms. But this term is from this cross product here, and so you're going to get this alpha in the cross product. And okay, I'm just going to write for the second link as well, 3. If you do link OB, you get AB I hat equals 33.28 I hat plus 0.25 alpha OB I hat. Okay, actually I'm going to skip that. You solve for alpha and you find your alphas, right? And then you substitute it in here and you get your tangential. But I really want to get to something else to help you guys with the homework. This link here, you guys can do the cross products and find everything, and you will find that this link is not rotating. You'll find that that omega is not rotating if you do all the cross products. But you can save yourself the time by knowing the rule that I told you guys before about instantaneous centers or just general plane motion. These two velocities from this guy is vertical, and the velocity from this guy is vertical, right? And they're not along the same perpendicular line. Their perpendicular lines never cross, which means that there's no instantaneous center, which means this guy's not rotating. So you can save yourself a lot of time and not have to do the cross product at both of these points and just find the velocity.
Sorry, I might be a little confused, but for A, when it rotates, doesn't it go to the right? Isn't there an X component to the right?
When this guy rotates?
Yeah.
Well, at this instant, the velocity of A is tangent, right? It's just straight up. It's tangent to the curve.
Because both links are in there.
Yeah, because if one link was at a different angle, then it would be this way, and then the link would be rotating. A couple other things. You guys will just have to come to office hours or go to Help Hub if you guys don't know this one. I don't have time to explain that one. This one with gears, you guys are going to see there's a lot of problems on the homework with circles and gears like this, and there was one on the last exam, or the last homework. And the easiest way to deal with these is to just approximate them as links, just like I did with this, where if you have a gear meshing with, a bunch of gears meshing with each other, you can just make it like they're links like this. And then it's just a link. It's just a link system. So I thought it would be fair to kind of show you guys that. Let's see if there's anything else. Also, I don't know why on this homework the previous professor put this problem. It's not a link, rigid body problem. But it is helpful for you guys because it's basically the first problem on the exam. Try to do this with the equation without looking at a solution. And test yourself, quiz yourself. Do I know how to do this now? And that leads me to your to-do list. Homework 8 is due tomorrow at midnight. Finish reading 15.4, start 9.5. That's just a review of moment of inertia for Wednesday. And I told you guys this last class. Each week I'm going to give you a problem to review from the first half of the quarter. There's a Tarzan work energy problem from extra examples. It was actually one of the exam problems from someone else's exam. So that's very representative of what you guys might get tested on. So practice that. Don't look at the solution. See if you know how to do it. If you don't, that means you need more practice. And then homework 9, it's only 2 problems. It's due Friday. And yeah.
Was it Tarzan one with the one where he swung and hit the branch?
Yeah, it is. I mean, maybe some people have already done that, so good for you. But
I think it was part of the midterm practice. Set.
Yeah, I think it was.
Thank you.
You didn't see it in there? Maybe it didn't come out of my notebook. Let me check.
Thank you.
Yeah, I didn't. You're welcome. I didn't pause this.